So let us try to solve this question 4-68. So in this chapter, in this question, there is a room. 4 by 5 by 6. And this room is to be heated by a baseboard heater. So we have attached like a baseboard heater. Usually it has water, hot water, and it keeps on warming air. Air comes in contact and leaves this room. Okay, so air inside the room. We have to condition this air to comfort uh, for our comfortability. So it is desired that a resistant heater to be able to raise the temperature from 5 to 25 Celsius. So initial temperature is T1, 5 degrees Celsius. Final temperature is 25 degrees Celsius. And within time duration of 11 minutes. And assuming no heat losses from the room and an atmospheric pressure of 100 kilopascal. So P, you can say P1 is 100 kilopascal. It's about atmospheric pressure, okay, which is 101 kilopascal. Determine the power. So we have to determine the power required by the resistance heater. So this power. So what we need to do here, power, W dot is power. W dot is power. It is by the heater. So electric. So now what we have to do here, if I go back to maybe this first law, Newton's, sorry, why am I saying Newton? His first law of thermodynamics, energy going in minus energy coming out equals to delta U, delta E. In this case, is delta U only, which is so delta U, small u. Can you tell me the formula for delta U? If you remember, I gave you this formula last lecture. Can you write that formula for delta U in the chat box? It starts from M and then it has something with that. Good. So M, yes, go ahead. Someone is trying to answer. Probably Sarah is trying to answer. So let us see. So M, yes, this is P V delta T. Good job. So this is the form. And now energy going in, it is in, let me tell you, there is no energy out because this room is not, this air is not lifting any piston, or it is not being compressed by any piston from the top. So there is zero work done on or by the system. But energy going in, this is E dot, I would say this is E in by the heater. So this is going in inside the, this is my boundary, so it is going in. You see my point? So Q in, I would say W, uh, WE in equals to delta U M CV delta T, and mass of the air is not given directly, but we are given with the pressure, we are given with the temperature, so we can find out. So let me tell you, if initial temperature is 5, can you write down P1 V1 equals to M or T1? Here P1 is 100 kilopascal and V1 is not going to change the room, so I will just write this down like this, 120. And M we have to find out. We have to find out the mass of air, or from the table can be found, and this is 0.287 kilojoules per kilogram Kelvin. And now T1 it is 5, but I will convert. Look, T1 should be converted into Kelvin, 278. So 278. Now if you do the math here, so let me rewrite here at the in the next line here. And I want to find out the mass. So if you open your calculators, 100 times 120 divided by 0.287 times 278. And if you solve for this, do you get 150 kilograms, 150.6 kilogram? You can verify and help your professor to whether you get the same value of mass. And if yes, then I will move forward. So let us see, there are just less students today, so I think it's okay. Okay, 150.4, 150. They both are correct. So now we are done, or we are almost done. This is our like energy, but we have to find out the same amount of, determine the required power of the sorry about that, resistance heater. So this is the energy going inside the air. Okay, guys, inside the air. This is going inside. So what, in how much time does it take to increase the temperature? It's 11 minutes. So if you know W electric in, which is mcv delta T, if you know that, can you find out power of that same energy in? Yes, you can. Look over here, mcv delta T divided by time duration, small delta T, and M is 150.6. CV, according to the table, um, it is given 0.718 for air. Uh, you can check it later on. And delta T is 25 minus 5, which is, I can write here 25 minus 5. You don't need to have worry about converting it into Kelvin first, because this rise or fall in Celsius and Kelvin, they are same. And 11 minutes needs to be converted into seconds. So if you do the math for this, you should be able to get 3.28 kilowatts. This is the power, electric power required to raise the temperature of air inside the room by the resistance heater. Do you guys understand that? And this resistance heater might be, I was saying for water, sometimes it's a water, sometimes electric, I'm not sure, but it's not our major concern. Major concern is that you have to find out the energy to increase the temperature of air. If you understood this problem, please type in yes in your chat box. If you have any question, you can ask your professor. Let me show you this table. This is a little blurry, but you can go ahead and see this at home. And one student says uh, he understands that. So let's see the next question. Let us solve another question here. Let us solve this problem. By the way, I was able to upload all the lectures on the YouTube videos. So please make sure you watch the old lecture if you want to. But I see you are regularly attending the lectures, so probably you don't need that much. People who could not attend, they can. Okay, let's solve this problem. A closed system containing 2 kilogram of air undergoes an isothermal process. So this is an isothermal process, and it raises, isothermal means constant temperature. Temperature for, maybe I can write it down. Okay. This is, there is the index n equals to 1 in this case, and the temperature is constant temperature. Is it expansion? The system undergoes a isothermal process from 600 to 80. So it's an expansion process. So I would say 1 to 2, 1 to 2. This is an expansion process, and initial and final temperature, they are same. This is 200 Celsius, or 473 Kelvin. Okay, guys, now let us write down the data given to us, 600 kilopascal. And I encourage you guys to follow the same procedure. First, write down all the information provided in the question, and then try to start writing down the equations. For example, first law equation, equation of perfect gas, and try to implement in the unknowns to find the unknowns. So determine the initial. So if final pressure is 80 kilopascals, okay, we have to find out what we have to determine the initial volume. So we have to find out the initial volume of this system. This is air. So I would say air. It is a piston expansion process. Determine the work done and the heat transfer during the process. So you have to find out the work done, energy, work done out, and the heat in. Now, according to Newton's, first law of thermodynamics, look over here, first law states that energy going inside the system minus energy leaving the system equals to delta E. This is a closed system, so it is delta U. Delta U, as you know, the formula is CV delta T. Now you will tell me, what is delta T in this case? If this is isothermal process, can you tell me the change in temperature in this specific case? Good. Sarah says it is 0. That's correct because it is isothermal process. The right hand side is equal to 0. If this right hand side is equal to 0, Q in minus W out, the boundary work equals 0. So whatever Q in goes inside the system, heat being supplied inside the system, it is used to lift the piston upward. I would say the boundary of this piston moves upward. Boundary out, I would say B out, to be more clear specifying. Even if you write on W out, but you should have a good concept that this is the boundary work done on the piston by the working fluid, which is air. So now up until here, this we have found this one. So we know that the work done can be found using the first law, sorry, using the what we call the isothermal process, or MRT. Both are correct. Now this is specific volume, and this is now in terms of, sorry, this is big volume. So because the answer will be in kilojoules. Now we do have pressure one, pressure ratio, we do have temperature, we do have R, we do have mass, we do not have. R, we already know that in this for air, this is from table A-2, air has 0.287, correct? So let me write the mass, we do know, sorry, the mass is given, which is 2 kilograms. So what else do we do not have? We do have 2 kilograms. R is 0.287, 473, P1 600 over 80. What do you guys get? So if you do the math, you can help your professor by verifying. I can do it in my small calculator. I got 547.05 kilojoules. So this is the work done by the system. Okay, this is work done in lifting the piston upward. The piston moves upward. Okay, guys, this is important that you understand the concept. The piston moves upward, gas expands, and the work is done. Now the first question says volume, initial volume. You know the first the equation, the gas equation, PV P1 V1 MR T1. So what is the volume V1? 2 times 0.287 times T1, which is actually isothermal. It doesn't matter T1 or T2, both are same. P1 is 600 kilopascals. Okay, guys, so I'm not changing it to 10 to the 3 because I wrote down this one as kilojoules. So if you solve for this, let me try to solve this for you. 2 times 0.287 times 473 divided by 600. So this is 0.4525 meter cubed. This is our initial volume of air inside the container. So we have found both answers. Please let me know if you, this is zoom out. I'm trying to zoom out, a little bit bigger zoom out. So can you tell me if you have understood this question? You can say yes, professor, in the chat box. Do you understand, guys? Pentrong, Sarah McGalley. Okay, good job, guys. That's very good. So you have understood this question. Let us solve another question. Some of the problems are from the homework, so it's okay. Even if you understand this from the lecture, so I would be happy that you understand the homework problems, and I would be able to share with you the solution for the quiz one, probably by before the end of the week. Okay, now make sure you prepare very well for the test two. Next week is the test two. Okay, I share with you. Did you receive an email and announcement about the test two? Please type in yes if you are uh, aware about the coming test. Okay, that's good. So let me know if you have any concern, questions, you can email me and I will try to answer your concerns. Okay, now let us solve this problem. Before we solve this problem, I want to show you that for the spring, this spring, when 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 the spring stretches, or if it is stretched, like it's big stretch or is compressed, so the delta x, it's like, I would say, force is directly proportional to the deformation in the spring. So now my concern is that it is a linear spring. It is like either you follow this expansion process like this is the linear spring. This is the what we call the, I would say, delta x, and this is a force. And either you follow this method or this, you see, this is contraction. Okay, volume, sorry, I would say delta x decreases, and this is f. So both cases, the line is a straight line. Okay, this is important that you understand. When you see such a question, spring, the work done by the spring, it would be a straight line for the assumption that spring behaves linearly, which is most of the cases true. Okay, spring loaded piston. This is the piston spring loaded device contains the this is the carbon dioxide, which is 1 kilogram. The mass of carbon dioxide is 1 kilogram. The system is heated, so we supply heat. Heat is being supplied. Heat is going inside the system. This is my system. Okay, this is my system, and the pressure, the temperature. Sorry, heated from initial pressure, which is 100 kilopascals, and temperature, I would say 25 plus 273 to convert it into Kelvin. 2000 kilopascals. 1000 kilopascals. So the question is, determine the total heat transfer to and the work produced by the system. Now you can see, we have to find out the total heat going inside the system and the work done out or in. We do not know. Let us see. So look, let me ask you, if initial pressure is 100, final pressure is 1000. So if I draw the diagram, PV diagram, like for a straight, so for a straight line, it will be a straight line. Okay, from 1 to 2. Okay, before, would you think this is a compression or expansion, or spring is expanding, or the piston is being depressed, or what do you think? Can you write down, is the carbon dioxide the new volume? Is it a um, compression process or expansion process? Look, over here, initial volume is, over here it is V1, and here with V2. V2 is, so if I say V2 minus V1, it should be negative because it is being compressed. The spring is, when you are supplying heat, the gases expand, and the spring force will push the piston downward. The piston moves downward, and the work done is negative. Like work out, I would say it would be negative, but work by the spring it is positive. So what is E in minus E out? That is equal to delta E of the system, which is delta U. Okay. And what is delta U? You know, CV delta T. Agreed? So, so we know that. And what is initial temperature is 25, final is 300. So can I write down delta T would be equal to 275 Kelvin. And CV for carbon dioxide. So if I do have the information, yes, we do have the information in this table. So let me copy this table here, A-2. This table is at the end of the book, A-2. So carbon dioxide. So we need to find out what is our CV, 0.657. If you take a look, CV for carbon dioxide is point. It's a little blurry because my PDF is blurry. Okay, now we do have CV, we do have delta T, we do have M. M for carbon dioxide is 1 kilogram. So that's good. So we can find out what is the right hand side of the equation. Okay, guys, now there is one thing. This energy out, I would say Q in, energy going in is Q in minus W out equals to delta U. So let us find out what is delta U. Can you help your professor? Can I write down M is 1 kilogram, CV 0.657, and 275? And if you multiply, what do you guys get? Please type in the chat box. So Hans is 178.75. Any other who seconds this answer? Okay, that's good. 180, 180.6. So I would assume this is 180.6 because two students have the same answer. So let me write down 180.6 at the moment. Okay, now it's okay. A little bit error is not a big deal. So now let me tell you, if you are given with the PDV, you remember work done is PDV. You remember that formula? We learned that formula. So what is the area under the this area under this curve? So this plot, I would say, let me show you this one over here. So I'm going to copy this again. And what is it, a trapezoid or rectangle plus triangle? So that's what this is V1, this is V2. Okay, now before we do this, I want you to solve for V1 and V2. So from P1, V1 equals to MR T1. This is a big V, okay? And now what is V1? This is in meter cubed. V1 can be found at 1 kilogram, or from the table it is 1.289. R is how much? 1 point, is it carbon dioxide? Point 0.889. It is 0.1889. I'm sorry, I was reading K. This is not R. This is R. And R is little blurry. 0.1889. So let me write down 0.1889. And temperature T1. Initial temperature is 298. Okay, guys, 298. Please open your calculators and help your professor. P1 is 100 kilopascals. 100 kilopascals. So if you compare your answer with this one, I would be very, can you verify 0.5629? Please check whether you get the same answer. Similarly, we can find out the second volume. Meanwhile, you can keep checking, okay? So these are the two volumes. So we know this volume is given. Now we have calculated this. Volume is calculated. P1 is given, which is how much? P1 is 100 kilopascal. So it's like a trapezoid. Area of the trapezoid would be the boundary work done of the trapezoid. So I would say this height. So P1 plus P2 over 2 times final minus initial. So you should get minus 250.1 kilojoules. And once you know this is minus sign says that the work is done on the system by the spring. Okay, spring is pushing this piston downwards. So work is done on the system. So I would write this down again. I'm going to write this down and find out my final answer of Q in. W out would be minus 250.1 plus 180.6. So open your calculators and do you get negative 69? Q in, if it is negative, it means heat rejected. It is not being supplied. It makes sense. So Q out, this would be Q out because of the negative sign. Please take a look at this question again. And if you have a concern or question, you can ask your professor or type in yes if you have understood this problem. Magali says yes. Sarah says yes. That's good. How about on hand trying and Marcus? You guys have you guys understood this problem? Please type in yes if you have. Oh, that's good. So I would say even you when you go home, try to see this video or try to solve this PDF. I'm gonna upload every lecture by tonight for your help. The material I want to give every material before you your exam. Like tonight, I would be able to do that. And I would, if I were you, I would start giving some time to prepare chapter 3 and chapter 4 and get good grades in this class. Okay, guys. So let's do one more problem here. So I would say let's do this problem. Okay, this is problem number 118. The mass is 10 kilogram and the working fluid we call is nitrogen. This is our uh, perfect gas. So it is heated from temperature T1 20 Celsius to temperature T2 and determine the total amount of heat required when this is done. So you have to find out Q in at a constant volume, mCV delta T, and isobaric process. Isobaric process means constant pressure process. So let me show you what I mean by that. For constant volume, energy in, first law, energy in minus energy out equals to change in the, and I would say delta E. But here it is not moving system, so it is delta U. When the working fluid is moving, it would be kinetic energy, or if it is at certain height difference, so you will consider that energy, potential energy. But in this case, this is not moving at all, so it is just a closed system, I would say delta U. So now energy going in, this is zero because of the constant volume. This is part A, that is equal to delta U. It is equal to mCV delta T. Okay, guys, M is 10. For nitrogen, let me see if this is written here. It is not written in this table, but I can write it down for you. In table A-2B, Cp equals to 1.045 kilojoules per kilogram Kelvin. Cv equals to 0.748. Now you can plug it in. So I can rewrite here Q in equals to delta U. What is delta U? mCv delta T. M is 10, Cv is 0.748, delta T is 230. So if you do the math, what do you guys get? Let me start from 230 times 0.748 times, I get 1070.4 kilojoules. This is in kilojoules because of the CV kilojoules. And let's do the other part. Part B, when the boundary is moving, isobaric process. Constant isobaric means, can you type in the chat box what is isobaric? Which thing is constant in isobaric process? Good. Sarah is correct. Pressure is constant. Okay, guys, now pressure is constant means the lid is having a weighted piston, which is a single way. This is a little bit strange diagram, but it's okay. Okay, now let me tell you. Energy in minus energy out equals to the energy of the system. Now here Q in, heat supplied. Heat is being supplied and work is done by the fluid inside. So PDV work out, boundary work out equals to delta E, which is delta U. And you guys know P work equals to PDV. And pressure in our case is isobaric. Pressure is outside, dV is here. So pressure delta V. So I can write down P V2 minus V1, U2 minus U1, and Q in. So if you do the math here, this is equals to delta H, which is enthalpy, H2 minus H1, big H, because this is in kilojoule. And that is equal to mCp delta T. M is 10, Cp from this from the table is 1.045. 1.045. Delta T is the temperature difference, which is 230. So that's it. So let's solve this, calculate this. 230 times 1.045 times 10. 2403.4. Oh, imagine this is just 2404 kilojoules. This is Q in. Do you guys understand this question? Please type in yes if you have understood this question. Okay, guys, now we have done most of the problems regarding this chapter. So now, do you want to have a mini break now or you want to have early release? Okay, students say early release. So let's do the next chapter. Our next chapter is, let me show you, where is my next chapter slides? I want to show you the slides. Chapter 5. Now, let me tell you over here, chapter 5 is about the open systems. Can you tell me the difference between closed system and open system in terms of energy and mass? What do you guys suggest your professor? What is open system? In an open system, look, here the mass cannot enter the container. In an open system, mass enters the device. Usually the devices are maybe like a tank, or the water is like, if you open water, go the mass is going in, m in, and you are getting water, m out, and this is how we do that. So the mass and energy analysis. You remember we did some questions for the previous, from the previous chapter, which we did the energy analysis. We were focusing energy analysis there, but we will also focus energy analysis, but with the mass including into this, like mass is also moving inside the device. So for example, if you have this is a compressor, steam enters and this is rotating and leaves after performing work. Steam m2 m dot, we usually call m dot in m. So you would see whatever mass comes in, that is equal to mass comes out. Why am I writing m dot? Because it is in kilograms per second, the mass flow rate. And you remember in the beginning of the lecture, if you remember, what is m dot equals to? M dot equals to, yes, rho, yeah. Look over here, I can tell you. So this is velocity, rho AV. Sometimes people also write down, they don't write down as rho, because rho can also be written as 1 over specific volume, area times velocity divided by specific volume. So let us try to understand this slide by slide. So I'm going to show you the slide by slide understanding of this question. Now, the objectives after you learn this chapter, you will be able to understand what is the conservation of mass principle. That mass remains conserved. Look, I just mentioned here a big picture. Look, whatever mass goes inside the device, the same mass comes outside the device. Mass coming in, mass leaving the system. And this is the, we also call it a steady flow in which the mass remains constant inside the device, but sometimes it does not leave the system. I tell you, you will study that if you have a nitrogen cylinder, you remember some, you might have seen some valves. These are valves are opened and the gas is compressed like in nitrogen cylinders. So where is the mass going in? So the mass entering the system, it is not going anywhere. So how would you solve this problem? We call this as an unsteady flow. Unsteady flow in which the mass keeps on changing with the passage of time. Unsteady. We will solve a few problems from this paradigm as well. And over here, look, this is a steady flow. Just a big picture. I'm just alluding it to you that what we are going to solve, see in this chapter. Steady flow. The mass inside the device. This is our device. This is compressor, rotary compressor like jet engine. Like you might have seen the small jet engine. So it's like over here. The air comes here. It's the same shaft compressor. I'm sorry. This is. It should have been not like this. It should have been like the engine. Compressor, combustion chamber, turbine. We are not concerned that much right now, but you will learn about the mass conservation principle. And you will also learn conservation of mass principle to steady and unsteady flow. I just gave you the example of unsteady flow, that filling up the nitrogen or even filling up the car tire. Inflating the car tire, it is an unsteady flow process. You are not, you are changing the mass flow inside the system, which is car tire, and that's why it is called unsteady flow process. Apply the first law for the open system. When you see control volumes are always used for open systems. So we make a boundary over here and we study this boundary. The volume inside the boundary is known as control volume. You will study about that. Control volumes, identify energy. Okay, so you will study about kinetic energy, flow energy. Flow, what is flow energy? You will learn about that. Solve the balance. You can study flow, nozzles, compressors, turbines, throttling, mixer heaters, heat exchangers. Apply the energy balance for unsteady flow process. So I'll teach you all these things in this chapter. Okay, let us try to follow the slides. As I mentioned, the conservation of mass means whatever mass comes inside the device, it is equal the same mass leaving the device. Or in the chemical conservation of mass, so mass or energy is a conserved property. Closed system, mass remains constant, and control volumes, mass enters the boundary. So you will see we call this as a mass conservation principle equation. So what is just a big picture? Whatever the mass going in equals to summation of mass flow rate coming out. For example, if you have a device like this, if you have a device which is a compressor, suppose this is a device. So the mass is coming here, the mass coming from here, the mass leaving from this side, leaving from this side, leaving from this side. So m dot 1, m dot 2, m dot 3, m dot 4, m dot 5. So when I apply this mass conservation principle, so whatever the mass flow rate from these are the ports. Okay, these are the openings. Some openings are related with the inside. It allows the fluid to go inside the device. Some openings are meant to be meant for all exhaust. So I'm going to write down the mass conservation principle here. M1 dot plus M2 dot. Look, all the summation have been completed here. The remaining three, look, 1, 2, 3. I'm going to write down on the right hand side. M dot 3 plus M dot 4 plus M dot 5. This is the conservation of mass equation. But this is not true when the fluid is flowing at a speed of light comparable to speed of which is 3 into 10 to the power 8. So the mass changes to energy is absolutely negligible in our case. So don't worry about that Einstein's theory of relativity in this case because we are not having the fluid at that much speed. So don't worry about this slide, but only thing which you have to take away is this formula. Please write down this mass flow rate formula. Rho V average area cross section. So if you have a pipeline, for example, in our house we have this pipeline like a plumbing line, water is flowing, and you see, suppose the diameter is 1/2 inch. So area cross section is 5/4 into the 1/2 square. And imagine the average speed of water, suppose 2 meters per second, for example. So the density of water is 1,000 kilograms. per meter cube. So you can tell me, Professor, look over here, rho A times area cross section, V average. So then you will do the math here. 1000 times whatever it is, 1/2. Actually, this should have been converted into, imagine this is in meters. This is so big. It should not be in meters. So I'm gonna convert it into, so this is how you would do that. Okay. I don't want to waste time to do the math here, but I'm just alluding it to you. Okay, look, the same equation I told you that it is written here. So mass flow rate in minus mass flow rate out, and summation. Usually the change in mass with respect to time is zero. This side is zero for the steady flow. This side is zero. So, so did you note down the same equation? All the mass force going in equals to mass force. So you see, 2 plus 3 gives you 5. You see my point? Have you understood the mass balance equation? Please type in yes if you have understood the mass flow, how to balance the mass flow rate in a device, inlet, outlet for a steady flow system. I'm glad that you have understood this important concept. Just alluding one more thing to you, which may not be here, but let me tell you, if whenever the mass goes in, the mass has a temperature. Every fluid has a temperature associated, and when you have a temperature, it means you have enthalpy. So energy carried by the mass, you will see later on, can be written by m dot 1 h1. You see my point? This is E dot. So if I tell you what is E dot out, you can tell me, Professor, look, m dot 2, sorry, this is m dot 2, okay, h2. This is how you will find out the kilowatts here. This is kilowatts power, and energy exiting, sorry, it's a power, not energy. Energy per unit, rate of energy 3 at the port 3, m dot 3 times h3. So this is just, I'm telling you that any mass which enters the port, it has a temperature associated with that, and because of that temperature, it has internal energy and it has a flow energy, P specific volume. That flow energy, U plus PV, what is that equals to? Can you write down in the chat box? Chat box, what is U plus PV equals to? That is equal to H. Okay, guys, this is enthalpy. Okay. Then we have volume flow rate. Usually volume flow rate is, but this is true for some special cases when you have incompressible flow. Then there is no such thing as conservation of volume principle for steady incompressible and steady incompressible. Though this is true, but for compressible flow, it is not true where the air compressor, you see, volume entering the system. Volume flow rate is 1.4. It should have been 1.4 here. But since air is compressible, therefore the volume reduces. When the pressure increases, volume reduces. Because of that, we don't have any conservation of volume principle, but we do have conservation of mass principle. But in case of incompressible fluids, for example, water, liquid, any liquid which is, liquids are incompressible. So we can apply that volume flow rate concept over there as well. But this is just to illustrate to you. Okay, now I told you that this enthalpy has two terms. One is internal energy, one is the P specific volume. This is pressure, P is pressure, and V is the specific volume, which is meter cube per kilogram. And when you see this is also the flow energy, we call the work to move the fluid. Like it, you can derive it, force equals to pressure times area, and work done equals to force times the distance L in moving the fluid from this in across L, and P times V. So you get P times specific volume. So you see my point, guys. Work of the flowing fluid, and the energy balance. Look, energy balance uh, is the same kinetic energy, potential energy, and enthalpy is also involved. Look, over here, we are also using enthalpy. Therefore, H plus K plus. So for control volumes, we have to consider enthalpy plus kinetic energy plus potential energy. But for control, so for the closed system, look, this is for the closed system. But for the fluid flowing, we have another term for the flowing fluid. Enthalpy is replaced. So look, over here is non-flowing. This is flowing fluid. We have enthalpy. Do you understand this concept? The basic concept should be clear. If it is clear, then you can solve difficult problems. Please type in yes if it is clear to you the difference between the energy balance of the closed system as well as the open system. Students are saying yes. I'm glad that you guys are learning. Are you guys learning? Okay, now look, energy transport by the mass m dot. This is the mass, but if you multiply by the rate of energy is m dot. So it's the same concept. Don't worry about this one. If it is integral, you mean you have to find out the changes integration. Usually we will be understanding we applying these two equations most of the time. Okay, and now energy analysis by the steady flow system. Steady flow is a flow in which the device contains energy and the mass throughout the time. For example, mass in the device is 1 kilogram air. After 1 hour you see it is 1 kilogram air. After 2 hours it is 1 kilogram air inside the device. It is not changing. Whatever fluid goes in, it comes out after filling up the whole device. This device has certain capacity, and the mass inside the device remains constant throughout the time duration. This is the steady flow, and energy as well as energy is also constant throughout with respect to time. So you see, look, I told you that any mass which enters the system contains the energy in terms of enthalpy. Enthalpy, enthalpy. You see my point, guys? I mentioned all this over here. So I'm gonna start from here next time. Okay, guys. Thank you. Have a good night. Bye bye.